All right, I want to take a look at triple integrals in cylindrical coordinates. So the idea is you've got some region in space. It's some three-dimensional thing. Of course, I'm drawing it in the plane, but anyway, it's supposed to be three-dimensional. You've got some function that's a function of x, y, and z. And you want to take this region and cut up a bunch of little pieces. For each piece, you take a point in there, you evaluate the function to get a height function, and then you multiply by the volume of the little piece. Now the thing is, in cylindrical coordinates, when you chop things up into little pieces, the question is, what do they look like? Well, cylindrical coordinates, let's see how well I can do this. Down in the xy plane here, you're going to have, from a point, you're going to change theta by a little bit, you're going to change r by a little bit, right? So that would make that a little bit of a wedge. And then you change z by a little bit. And so you end up with these little pieces that look like that. And then, how much volume is there? Well, like polar coordinates, it's going to depend on where r is, because with this little angle here, d theta, it depends on where you are. This length here, dr, would stay the same, but you can slide in or out, and the amount of area that you have is going to change. So the thing is, the area of the base, this little dA, is still like it was in polar coordinates. It's r dr d theta. But then you're going to multiply that area times the height here, dz. So this little bit of volume is r dr d theta dz. I said z. Or any order you can multiply those. Generally, the way we do it is the z almost always ends up on the inside. And then r, and then theta. And the reason that is that for the most part, when we look at functions and graphs of functions or whatever, when we deal in cylindrical coordinates, we almost always think of z as a function of r and theta, just like we usually think of z as a function of x and y. Likewise, in polar coordinates, we usually have r as a function of theta and not the other way around. I have to admit that if you're really looking for some interesting things to do, try looking at polar coordinates where theta is a function of r, or, well, maybe in class we'll do some cylindrical coordinates with z not being the dependent variable, but maybe let it be independent. Look at what we can do with some things there. But anyway, the idea here is the volume element is r dz dr d theta. So when you have a triple integral of some function of x, y, and z dv over the region E, then what you want to do is you want to set this up as the integral of, you got to convert to cylindrical coordinates here. X is r cos theta, y is r sine theta, and z is z. And then the dv is r dz dr d theta. See if I can actually write it. There we go. R dz dr d theta. And then you've got to set up your limits appropriately. I'll put question marks there just because I don't know what they are yet, but there's certain limits. And like x, y's, and z's, when you set this up as an iterated integral, the outside integral, these limits have to be constants. The next ones in have to be functions maybe of that variable. Or constants. And then the inside limits in here and here could be functions of both of those two variables, or they could be constant. Okay. Let's do an example here. The example I want to do is I want to find the volume inside of the sphere x squared plus y squared plus z squared equals 2. That is above this paraboloid, z equals x squared plus y squared. Now, triple integrals can be used to find volume by integrating 1 dV. So what I'm looking for is the triple integral of 1 dV over this region that I'm talking about. Well, let's see here. X squared plus y squared plus z squared equals 2 is a sphere of radius square root of 2. Okay. So inside of that, and that's above this thing. So I've got this paraboloid opening upward here. And this goes up. Those two things will intersect in some circle up there somewhere. And it looks like I'm looking for the volume of that thing in there. So bounded below by the parabola and bounded above by the sphere. Okay. So in order to do this, I'm going to integrate 1 dV. Now dV, I'm going to do polar coordinates here just because this is a nice region. When I think about projecting this down to the xy plane, in the xy plane you're talking about some circle in there, and that for every point in that circle I'm bounded by the paraboloid there and the sphere at the top. So so doing this in polar coordinates is going to be good because it's, well, each of these turns not polar coordinates. Well, polar with z, so cylindrical coordinates. These become nice functions here. So the function on the top is going to be z squared equals 2 minus r squared, because x squared plus y squared is r squared. And likewise, the function on the bottom is going to be z equals r squared, because x squared plus y squared is r squared. Okay, so dv is r, dz, dr, d theta. This region down here in the xy plane, or maybe think of the r theta plane, whatever, you're going all the way around, so 0 to 2 pi on theta. R goes from 0 out to wherever those two things intersect, and I guess we haven't figured that out yet. Well, where do those two things intersect? Well, x squared plus y squared is z, so I'm going to substitute that in there. I've got z plus z squared equals 2, so z squared plus z minus 2 equals 0. Factor that. I've got z, what do I have? Plus 2 and minus 1. So z equals negative 2 or z equals 1. This one's fascinating to me. Z equals 1, I think, is what I'm looking for here. So when z equals 1, then r squared equals 1, so r equals 1. So that's apparently a 1 right there. Okay, but what's this z equals negative 2? I mean, this the parabola goes up. The parabola doesn't even get down to negative 2. The sphere doesn't even get down to negative 2. Like, what? But the thing is, if z is equal to negative 2, then r squared is equal to negative 2. And you got negative 2 plus negative 2 squared. Well, that's negative 2 plus 4. That's 2. Right? And you get the equation works. So it looks kind of funny, but if we did this with complex numbers, then apparently something else is happening down here. But stick with real numbers for now. So theta is from 0 to 2 pi. R is from 0 to 1. And then z goes from the bottom function to the top function. The bottom function is r squared. The top function is the square root of 2 minus r squared. Okay. Integrate with respect to z. This is just r times z evaluated between r squared and the square root of 2 minus r squared. Plugging in, I've got r times the square root of 2 minus r squared minus r squared. So either you can have the r multiplied by both of those or factored out. And then there's this double integral dr d theta. Wow, what just happened? dr d theta, 0 to 1, 0 to 2 pi. And at this point, I think you can do this just fine. Since there's no thetas in here, this is just going to be 2 pi times the integral from 0 to 1 of r times the square root of 2 minus r squared minus r cubed dr. And you could do that one by hand with a u substitution, not too hard, but then plug it into your calculator. There's another way to do that. So anyway, there's that double integral. And yeah, I'm not going to have enough time to do another one in this video, so I'll make another video for the next example.